afternoon, good morning, good evening, class. It is a brand new day. We're starting a new chapter, or not new chapter, new section in chapter 15, where last Friday we were talking about equilibrium reactions, reversible reactions, the nature of those reactions, how you can manipulate your equilibrium constant based on the reaction, what it means. There were a lot of big general topics. So today what we're going to be talking about is the spontaneity of these reversible reactions and how our K can be useful in telling us the direction of the reaction if it is reversible. Like, what does spontaneity mean really in the context of this reversible reaction concept? All right, so there are a couple of different ways that we can predict spontaneity and what it means in a reversible reaction. So if we want to predict the direction of a reversible reaction, whatever direction it's going to spontaneously move in. So spontaneous, again, in this sense, means that the reaction requires no continuous energy input. So the reaction itself, you don't need to force it to move in any direction. It will spontaneously shift either from reactants to products, or in this case, also possibly from products to reactants, all on its own spontaneously. Okay, so there are two different ways that we can predict the spontaneous direction of a reaction. Either we can use this concept known as the reaction quotient, which we will be describing shortly, or we can use our good old Gibbs free energy as was described in chapter 14. We are going to be looking at a slightly modified version of Gibbs free energy, a version of Gibbs free energy that includes the equilibrium constant K. The main premise, though, like why we care about this, is that once your direction of the reaction is known, an equilibrium concentration for reactants and products can be found from initial conditions. So what we looked at last Friday was how do you find, an equilibrium concentration of X if you're at equilibrium, if you already know Kc. So we learned how these two pieces connect. Today we're going to be looking at, well, if you don't know the equilibrium conditions, if you just have a Kc from initial conditions, how can you predict what these equilibrium concentrations are going to be? All right, so our first concept is the reaction quotient. This is represented by a variable Q with a lowercase c, in this case also representing that we are working with concentrations. Now our concentrations, are corresponding to the subscript of the C, does imply that there's like a QP or other forms of the reaction quotient that mirror the equilibrium constant. We'll be working with QC most of the time. So this is the ratio of the products and the reactant concentrations for a reaction that is not yet at equilibrium. So the equation itself looks very similar to C, right? K. This whole reaction looks like Kc. We have products raised to the exponent of their stoichiometric coefficients, all divided by reactants raised to their stoichiometric coefficients. The major difference is that this calculation for Q is not at equilibrium, since the forward rate is not necessarily yet equal to the reverse rate in this reversible reaction, which is why in the expression for QC we have these little subscripts of I. These mean initial conditions. We are not at equilibrium. Initial conditions. All right, we are not at equilibrium. All right, but the magnitude of Q relative to K, right, that's what we're going to be looking at down here, points 1 through 3. This Q versus K can tell you something about the direction, though, of your reaction and which direction it's going to spontaneously move. All right, so first let's look at situation 1, where Q is less than K. If your Q is less than your K, in other words, if your initial conditions ratio of products to reactants is less than that at equilibrium, well, what this means is that in order for this value of Q, numerically speaking, if we're kind of comparing numbers, our Q is only going to be smaller than K if we have too many reactants, right? So if we have too many reactants, this means too many reactants. It means that your reaction must shift forward. Your reaction must shift from reactants, shift forward. It must shift from reactants to products in order to remove some of the reactants and also create some more product. All right, so just cleaning up the slide there a little bit. So in our first case scenario, this is, again, just to rewrite this for the sake of comparison, shifts forward. All right, so in our second situation that we're going to be looking at, what happens or what does it mean when your Q, your reaction quotient, is greater than K? Well, what this means is that initially, if your Q, again, in terms of number, in terms of magnitude, is too big, it must mean that you have too large of a numerator. Now, if you have too large of a numerator, this means that according to the natural balance of this reaction, you have too many products. All right, and if you have too many products, then the reaction must spontaneously shift in reverse. It must shift away from product. Reverse. It must shift away from the product and more towards the reactant in order to balance this product to reactant ratio. Right, so in first situation, if your Q, represented again by initial conditions, is too small compared to your K, your reaction must shift forward. If your Q was too large, then your reaction must shift backward. So this is going to tell us then again which direction the reaction is going to shift in order to reach equilibrium, right? It's all about reaching equilibrium. There. This is what we're always trying to get to, or this is the state that we are trying to get to. Since reversible reactions don't, again, have like an end, you don't reach a point where you run out of reactants. Instead, what's going to be happening is the reaction is aspiring to reach equilibrium instead. This very steady state where your rate forward is equal to rate reverse. All right, the last case scenario then, scenario 3, if your Q is equal to K, well, again, this is sort of like a Goldilocks situation. If your Q is equal to K, you don't have too many reactants, you don't have too many products. In fact, you have reached equilibrium. Your forward rate is equal to your reverse rate, and there is going to be no shift. There, no shift. Okay, so our reaction quotient then is useful to us in that it tells us from initial conditions where we're going to be going in order to reach equilibrium. So the reaction quotient, this concept can also be visualized. Right, we also had a similar visualization when describing equilibrium in the first place, this reaction where our N2O4 is decomposing into 2 nitrogen dioxides. There's going to be a point where your reactant, is going to be decreasing in concentration, your product increases in concentration, but then there's a point where your reaction is going to, if it's reversible, hit this nice equilibrium steady state. So concentrations can be monitored as time passes to observe this type of spontaneity. So for example, let's look at what the QC for this reaction is going to look like. And our QC is going to be calculated by looking at the concentration of our NO2 squared, all divided by the concentration of our N2O4. And these are going to be at some point of initial conditions. So initial, it's really important to recognize, initial does not necessarily mean T equal to 0. It's going to be anywhere along the spectrum right up until we hit where equilibrium is reached. So it's going to be important for us to define exactly what our initial conditions look like. So let's look at a couple of different points on this chart and see what the data is telling us. So the first point we'll look at will be, sure, T equal to 0. Why not? This is a really standard sort of T equal to 0. 0 seconds right at the beginning of the reaction. It's a very simple, straightforward, consistent way to measure initial conditions. So initially we have a 0.2 molar N2O4 solution, and we have none of the, we have 0.2 molar of the NO2, we have 0.2 molar of our product, and we have none of our reactant. So of course, if we don't have any reactant, well, it would stand to reason that the reaction is going to have to shift backwards in order to hit this. And this is exactly what our Q is telling us. Our Q at T equal to 0 is going to be, right, we have some concentration, 0.2 molar. We're going to square that, and we're going to divide by nothing. Well, if you divide by nothing, that means that your Q is going to be infinite, which is exactly what we see down here underneath the graph. And if your Q is infinite, this is definitely bigger than K, right? Regardless of what K could be, your equilibrium constant, infinity is bigger. It is infinitely bigger, which means that your reaction has too much product and must shift backwards in order to regenerate some of this reactant here. And that is exactly what we end up seeing, right? The concentration of your product goes down and the concentration of your reactant goes up. At some other point T in the future, we can try and double check, like, are we at equilibrium yet here? So this point is going to be when your concentration of reactant and product are both equal to 0.08 molar. And so again, one common misconception is that equilibrium means that your concentrations are equal. This is not necessarily going to be true. All right, so let me clean this up a little bit. All right, and we can rewrite real quick what our QC expression is going to be equal to. It is going to be concentration of products squared. So the concentration of our product is that 0.080 molar. We can square that. And this is going to be divided by a 0.080 molar. Now, what ends up, what Q ends up mathematically equaling is a 0.080. And for anyone who is keeping track, the equilibrium constant for this expression as it is written is 4.65 times 10 to the negative 3. So what this tells us is that, yes, even though we have equal concentration of product and reactant, we are not at equilibrium since our reaction quotient is still greater than our Kc, this 4.65 times 10 to the negative 3. So we are not at equilibrium yet. So if we let the reaction progress, again, what this is telling us is that we still have too much product. Our reaction is still going to be shifting back towards our reactant. And so as the time increases, we see that eventually we hit this steady state where, yes, in terms of concentration, we have more N2O4, but what's important is the ratio between the N2O4 and the NO2, and that we have more of the NO2, which is what we would naturally expect based on our equilibrium constant. This is the constraint that tells us what is the balance between reactants and products for this given reversible reaction. Okay, so we can also use Gibbs free energy, as was previously stated, to determine what is the direction of our reversible reaction. So the reversible reaction that is not at equilibrium will spontaneously move towards equilibrium, which is what we have been talking about, according to what its Gibbs free energy is going to be equal to. And so here we have this new equation present. What this equation represents, we'll start our way from the right and move to the left. So we have a Q that is present inside of this natural log, which stands for the reaction quotient that we have been talking about. Reaction quotient. We have T for temperature. This has to be, as one would expect, in Kelvin. And we have our gas constant R. So this gas constant R, since we are working with an energetic form, right, Gibbs free energy, should be equal to the 8.314 joules per mole Kelvin version. Okay, and now here's where we can differentiate between these two Gibbs energies here. Now the Gibbs free energy that is on the right-hand side of this equation does represent our standard Gibbs. And this standard Gibbs is going to be at 25 degrees Celsius. This is not a STP kind of standard. This is a different standard temperature. This is the same standard temperature that all of the Appendix 2 data is in. So we can use the Appendix 2 data to calculate what is our standard Gibbs free energy at 25 degrees Celsius. Now this modification, this additional piece, this RT natural log Q, tells us what is the balance of reactant or product to reactant, what's that ratio And what is the weight of it? That's what this RT stands for. And so the balance between our Gibbs free energy calculation and this Gibbs energy component on the right-hand side that we're kind of adding, this modifier based on initial conditions, will tell us this new Gibbs free energy that's not necessarily at standard conditions. The temperature that can go into T does not necessarily have to be at 25 degrees Celsius. This delta G naught does have to be at 25 degrees Celsius. So as temperature changes, as our initial concentrations change, this is going to give us a new meaning to our delta G. All right, so let's talk about what this new delta G then stands for, what it represents. All right, so the delta G, if our delta G, kind of scenario 1, is negative, what this means is that the reaction will be spontaneous in the forward direction. So the reaction will shift from reactants to products because the balance between the Gibbs free energy in the standard conditions here and the modified conditions, either a modified temperature or modified initial conditions, there is something that is out of whack, something out of balance, and so your reaction is going to have to shift in the forward direction to create some more products in order to balance out this Gibbs free energy. All right, so again, the delta G's that we are looking at here are the delta G's that we have calculated on the left-hand side of the equation. If your delta G is greater than 0, if it is positive, your reaction will still be spontaneous. It's just going to be in the reverse direction. You have too many products. You're looking at a situation where your products need to shift backwards into reactants. So we might even be able to predict that if we had calculated the Gibbs free energy for the example we just looked at, we would have found a positive Gibbs free energy, since we saw based on concentration balance, your reaction has to shift in reverse. Now, the magical situation where your delta G is equal to 0 corresponds to a situation where you are at equilibrium. Your product to reactant ratio is balanced, your temperature is balanced, it being the reaction, does not have to shift in any way. Your Gibbs free energy calculation is good. All right, so when this equation or these concepts are going to be useful to us, because you see that this new Gibbs free energy equation does have a reaction quotient in it, so you might be asking yourself, well, like, when would I want to use this instead of just looking at Q versus K, which is what we just talked about? Well, there are going to be situations where you don't know your equilibrium constant. You don't know K. So if you don't know K, but you do have the means to calculate this Gibbs free energy at standard conditions, you can now calculate the Gibbs free energy for your reversible reaction and use the value whether or not it is positive or negative or equal to 0 to tell you whether or not your reaction is going to be spontaneously progressing in a given direction or if it is already at equilibrium. All right, so let's look at an example calculation here. So we have some information that has been provided to us, like our delta G naught, our standard conditions for delta G of reaction at 298 Kelvin is found to be 16 kilojoules per mole. It doesn't necessarily matter what the reaction is, but we know what its Gibbs free energy is equal to. So if your reaction quotient, your Q, balance of products to reactants, is found to be 0.012, is the reaction spontaneous or spontaneously continuing in the forward or the reverse direction? So since no other temperature is given to us, it is safe to assume that our T, our temperature, is also going to be at 298. So we're just looking with our current Q at standard conditions at this 25 degrees Celsius, is your reaction going to progress forward or backward? All right, so we can use the equation that we just learned. Our delta G of reaction is equal to a delta G naught of reaction plus RT natural log of Q. So the standard Gibbs free energy was given to us, this 16.0 kilojoules per mole. Our R, again, is given to us, this 8.314. Now I am going to shift this into kilojoules, so I'm going to tack on a times 10 to the negative third to make this equal to a kilojoule per mole Kelvin value. Temperature, we're going to say is that 298 Kelvin. So kelvins are going to cancel out here. We can see kilojoules per mole are going to be working together. Not necessarily canceling out, but they will be giving us a final delta G that is consistently going to be in kilojoules. So again, always going to be wanting to look at our units here and make sure that everything is playing together nicely. Now Q, much like K, does not have a unit associated with it since we are looking at a ratio of molarities or a ratio, again, of whatever your concentration unit is. It's safe to assume that they're going to relatively cancel out. So this Q does not have any type of unit associated with it that we'd have to necessarily worry about whether or not it's going to like play with the rest of them. But here we have a way now to calculate what the Gibbs free energy is going to equal. So whether or not you want to, again, shift your Gibbs free energy value into joules to match your equilibrium constant here, or not equilibrium constant, your gas constant, your R, or if you want to shift your R to match your delta G, just so long as they are consistent, it should be fine. So if we perform this calculation then, taking 16 plus this entire R times T times natural log of Q term, we should find a value that is equal to 5.0 kilojoules per every mole. So what we're looking at here is that the Gibbs free energy that we just calculated is positive. It is greater than 0. So what this tells us is that our reaction is going to be spontaneous because it is not equal to 0. And it's going to be spontaneous in the reverse direction. This Gibbs free energy is positive, meaning that progressing in the forwards direction will only make the reaction less stable. A Gibbs free energy is going to, it represents like spontaneity in the forward direction if it is negative. That's going to be consistent with the Gibbs free energy as we talked about it in chapter 14. So here it's going to be spontaneous, our reaction will be spontaneous, but spontaneous in reverse. All right, so let's say, again, because I had said that this version of Gibbs free energy equation is useful to us if we don't know K. Well, can we use this information to find K? What is the equilibrium constant for the hypothetical previous reaction? And we can use our our equilibrium constant to determine also whether or not reactants, products, or kind of both are favored. In other words, like what's the balance of products to reactants as we had talked about on Friday. All right, so what's really cool about the previous equation, as we had talked about it, is that delta G of your reaction, not delta G standard, the delta G as it is calculated. If it is equal to 0, what this means is that you are at equilibrium. So if your delta G is equal to 0, well, you're at equilibrium, which means also that your Q is equal to K, right? If you're at equilibrium, both of these concepts were stated to be true, which means that in your Gibbs free energy equation, where your delta G is equal to 0, you have a delta G naught of reaction plus R times T times natural log of K, right? At equilibrium, Q is equal to K, which means we can plug K into this equation here, as we have also inserted 0 for our Gibbs free energy. And now we have a way to calculate K if we know what the Gibbs free energy at standard conditions and the temperature of the reaction is. And this is also going to be true for every reaction, not just this hypothetical case, since by definition, your delta G is equal to 0 at equilibrium, and also Q is equal to K at equilibrium. All right, so let's insert the data from our previous example. Let's see. So this time I'm going to work through in joules. So we have a 1.6 times 10 to the 4th joules per mole, just so we can see how like both versions of this kind of work out. But again, just so long as your units are consistent, doesn't really matter. Your R is going to be 8.314 joules per mole Kelvin. Temperature, we're going to assume that we haven't changed it since the temperature was not stated to change. And last but not least, we have a natural log. Wow, that's a bad N. Natural log of K. And all of this is going to be equal to 0. So now we have a way to algebraically rearrange and solve for what K is going to be equal to. I leave this algebraic exercise to the viewer since we you're going to have to be able to perform these algebraic calculations on your own, but I will give you the final answer just so you can compare or have something to compare to. Your K, your equilibrium constant, is going to be equal to 0.00157. Now this value is definitely less than 1. This represents then, this equilibrium constant represents a ratio of products to reactants where products are not being very heavily favored. Your reactants are being heavily favored. Since this is less than 1, it means that in your equilibrium expression, you must have a very large denominator, and your denominator is where the concentrations of your reactants can be found. Okay, so if you have any questions at this point, do not hesitate to shoot them my way. Whether it be on Discord, via email, whatever the situation is, I look forward to hearing any type of question that you might have. Okay, so now that we have a way to predict which direction your equilibrium is going, or your reversible reaction is going to shift, all depending on how close or far away you are from equilibrium, let's tie in the idea of being able to calculate equilibrium concentrations if you know initial concentrations. Right, so this type of process we're going to talk about using ICE tables, which I'll lay out this acronym in a second, because yes, ICE in this case is an acronym. The kind of parallel to previous conversations we've had that have to do with stoichiometry is before we would start with a limiting reactant. Right, so let's do a colon here. Limiting reactant. And from your limiting reactant, you could get some type of theoretical yield. So that's sort of like what we are going to be learning now, only it's going to be a stoichiometric process for reversible reactions. Again, looking at a limiting reactant and a theoretical yield, as we've learned before, does not work for this case. Since these reactions are reversible, there is no limiting reactant, there is no theoretical yield as we have previously talked about. So we're going to have to learn a new way to calculate what is the end state going to look like. What are these equilibrium concentrations going to be equal to? So here's where we're going to introduce the concept of an ICE table. Now, you might have learned a different version of this in high school, or you've never seen it before, or you've learned how to calculate equilibrium concentrations without something called an ICE table. All of those things are totally fine. This is the method that works best for me, and this is what I am going to be passing on to you guys. I would definitely encourage you to read through the textbook, though. Find, not necessarily alternate means to calculate equilibrium concentrations, because I don't want you guys to have to be spinning your wheels on something you don't necessarily need to know or might be incorrect. But if this seems very strange and foreign to you, what I am going to encourage you to do is get practice under your belt. Practice, practice, practice. With practice, this type of problem will go faster and will become easier. All right, so let's lay out how to perform this type of calculation. So we're going to use this ICE table to calculate our equilibrium concentrations of reactants and products if we know the initial conditions and a Kc or Kp or whatever type of equilibrium constant that we are working with. So the I in the ICE table stands for our initial conditions. Right, this is our starting point. This is like the starting point on our treasure map. Our C is going to represent the change, whether or not your reaction is going to be, let's say spontaneous. We'll keep the language consistent. If it's going to be spontaneous in the forward or reverse. So we're going to be using the concept of our Q or our delta G to figure out what is the change of the reaction. This is going to tell us the progression of the reaction as it continues. And eventually we will hit X marks the spot, which is what E stands for. This is going to be equal to our equilibrium conditions. And I want to keep the language general with the word conditions, since we could be working with pressures, both initial pressures and equilibrium pressures. This process is going to work mathematically the same way. So the best way to learn this method that we're going to lay out, where we're going to use our initial conditions, observe some type of change, and calculate equilibrium conditions, because so far we haven't seen anything too remarkable, the best way to learn, in my opinion in this case, is to do. So we are going to do an ICE table problem. We are going to lay out the method that we are going to be using to solve for equilibrium conditions for reversible reactions. So what will the equilibrium concentrations be for the following reaction, both reactants and products, provided that we know the initial conditions where we have an initial concentration of H2 that's equal to 0.1, an initial concentration of I2 that is equal to 0.2, and an initial concentration of HI equal to also 0.1. So in this type, or in this example problem, we're going to be starting with both reactants and products. And this work is going to be, I guess the best way to say it is the most complicated version of this problem. There are simplifications. We will talk about the simplifications afterward, but if you know how to follow the most detailed steps for the hardest problem, you will be able to extrapolate and figure out how to solve the easier problems much, much more easily instead of having to build up to this, because the process is going to look the exact same for every problem. So the way to start, here we have our reversible reaction, our H2 being added to our I2, reacting reversibly to give us 2HI. And here's the equilibrium constant, Kc, presented. We can see it's equal to 45.9, meaning that we have a pretty equal balance between reactant and product in this reversible reaction. So where we're going to start, we're going to lay out what we know, our initial conditions. So our initial concentration for H2 is 0.1 molar. Our initial concentration for I2 is 0.2 molar, and our initial concentration for HI is 0.1 molar. So notice that I'm just laying out these concentrations right underneath the reactants and products in our chemical equation. We're treating this almost like a table, right? The header is up above, and our row labels are going to tell us what we're filling in. Well, the next row label is the C. This is the change that we're going to expect to see, which means that we need to figure out in which direction is this reaction going to shift. So our very first step in solving for what the equilibrium concentrations will end up being is to figure out what is our Q. Since we have an equilibrium constant K, we can compare Q to K to figure out which direction is the reaction going to shift. Is it going to move spontaneously in the forward direction to create more product, or is it going to move spontaneously in the reverse direction to create more reactant? So let's set up our Q. Our Q is going to be equal to, and again, we're setting this up in the exact same way that we set up the expression for the equilibrium constant. It's just now we're using the initial conditions. We don't know if we're at equilibrium. I mean, hey, if our Q ends up being equal to 45.9, problem's done. I'm sure you could tell, though, by my preface into this problem, that is not going to end up being the case. So the concentration for our HI is going to be squared since we have a 2 in our equilibrium reversible reaction here. Concentration of H2 is going to be multiplied by concentration of I2 in the denominator. Plugging in the values that we have, our concentration of HI we can see initially is a 0.1 molar, and this is going to be squared. We will divide this all by 0.1 molar times 0.2 molar. What this ends up equaling, this gives us a K, or a Q, that is equal to, oh no, where'd my mouse go? Down here, there we go, 0.5. Now this value for Q is definitely less than our value for K. Q is less than K. Now, since Q is less than K, what this tells us is that we don't have enough product. We have too much reactant. And because we have too much reactant, our reaction is going to shift or react spontaneously in the forward direction. We are going to be losing reactant, and we are going to be gaining product. Now, the exact amount of this loss we do not know, but we can figure it out. The change that we can predict so far, we are going to be losing reactant, hence why there are these negative signs here, and we are going to be gaining our product, hence why there's a plus sign here. The exact change, since it is an unknown, we are going to leave as a value of X. We are going to lose a certain amount of reactant, where the change or loss of both of the reactants is going to be equivalent, since we have a 1-to-1 balance in our reactants. However, as the reactants react and we end up generating product, we will gain twice as much product for every unit of change that the reactants make, since we have an coefficient of 2 in front of our HI here. So this coefficient of 2 is what ends up getting plugged right in front of this X. So what this tells us is that at equilibrium, we will end up with a 0.1 minus X molar solution or collection of this H2 gas. We will have a 0.2 minus X molar collection or sample of this I2, and we will have a 0.1 plus 2X sample of our HI. So all I've done is added up each of these columns where 0.1 minus X gives us this equilibrium concentration for the H2. The 0.2, our initial condition, minus the change of X is going to give us the 0.2 minus X, and our 0.1 molar plus 2X gives us this 0.1 plus 2X down below. Now, at first glance, it would appear as though like, okay, well, what do I do with this information? I didn't really solve for what the equilibrium concentrations are equal to because I still have this unknown of X here. But what we have now is an equation that we can set up based on equilibrium conditions. Since we know our equilibrium constant is 45.9, and if we were to set up an equilibrium expression where our equilibrium concentrations get plugged in here, well, we can see that we have one equation and one unknown, and that one unknown is the X. If we can solve for X, then we can solve explicitly for what the change is going to be from initial to equilibrium, and therefore we can solve for the equilibrium concentrations directly if we can find X. Okay, so I have set up this kind of blank slide I'm going to be working on. We're just following up from the same work, but I want to be able to like flash backwards to it if I need it. So let's set up our equilibrium expression. Our equilibrium expression is going to be equal to concentration of product HI squared at equilibrium, right? That's the defining feature of K versus C. Now we are going to assume that we are at equilibrium. The change has occurred from our initial conditions to give us a stable, reversible reaction. The H2 concentration at equilibrium will be multiplied by the I2 concentration at equilibrium. And we may not know what the exact equilibrium concentrations are, but we do know initial plus the change for the product, where X, again, is that unknown change. We know 0.1 minus X for the reactant H2, and 0.2 minus X for the reactant I2. And all of this is going to be equal to 45.9. So here now we have that equation that I had mentioned, this one equation based on equilibrium, knowing or hypothesizing what our concentration change is going to be, and setting that equal to what we know our equilibrium constant is equal to, 45.9. So from here, it's just a matter of algebraically rearranging and solving for X. So I'm not going to show every step, but I will show some of the steps, kind of setting up this problem. First, we're going to take the denominator and multiply it up into the numerator on the other side. So we will end up with a 0.1 plus 2x squared. This will be equal to 45.9 times 0.1 minus x times 0.2 minus x. All right, the next step afterwards, to solve for x, right, because the goal is we want to get x on one side and all of the rest of the numbers on the other side. So let's set up the left-hand side of the equation into something that we can work with to actually solve for x. We are going to set this up, since the squared here just means that we're taking the same thing in the squared twice, multiplying it together. We're going to take 0.1 plus 2x, multiply it by 0.1 plus 2x. And all of this is going to be equal to what was previously on the right-hand side, 0.1 minus x, 0.2 minus x. So from here, what we can do is, if you heard this acronym in high school, awesome. If not, then what we're going to do is the process of foiling. So we're going to combine these like multiple terms here. So we're going to take the first term, multiply it by the first term here, plus the first term by the second term, plus the second term by the first term, and the second term by the second term. And what this ends up giving us for the left-hand side is a 0.01 plus 0.4x plus 4x squared. This is going to be equal to 45.9 times, we're going to do the same thing for this term on, or these two terms that are being multiplied on the right-hand side, first, outside, inside, and last, the process known as foiling. So we're going to add all of these terms up as well. That'll give us a 0.02 minus 0.3x plus x squared. So here now we have nearly set up this equation to solve for x, and the goal, is going to isolate x. Well, we can't just straightforwardly isolate x since we have some squared terms here. What we're going to actually end up doing is setting up a quadratic equation instead. So if we pull everything to one hand side of the equation, leaving only a 0 on the other, what this leaves us with, or sets us up to solve for, is a 41.9x squared minus 14.17x plus 0.908. And all of this is equal to 0. All right, so just to recap what we've done so far, we set up our equilibrium expression so that we can solve for x. We started rearranging to try and isolate x, but because we ended up with these quadratic terms, right, this square, even though we still have an x that just has an exponent of 1, the way to solve for x then here is to set up a quadratic. In other words, we are going to be using the quadratic formula to be able to solve for x here. Now, if you haven't written this down yet, or if you want to perform more of the algebraic steps in between, definitely pause the video because I am about to erase everything, so I still have a blank sheet to be working with. All right, but I will rewrite what we just had, 41.9x squared minus 14.17x plus 0.908, and all of this is equal to 0. So the quadratic equation is going to allow us, so long as our equation is written in this form where we have some ax squared plus bx plus c all equal to 0, what this is going to enable us to do is use the quadratic equation, which is a means to solve for x so long as your equation is set up like a quadratic, where your x is going to be equal to negative b plus or minus square root of b squared minus 4ac, all divided by 2a. So for anyone who graduated from high school, glad that algebra was behind you and thinking you would never see the quadratic equation again, I am sorry. We are going to be using this not as much as what chapter 15 initially would have you believe, but we are going to be getting lots of practice with this just in case you need to use it. So our b in this case is going to be equal to 14.7, our a is equal to 41.9, and our c is equal to 0.908. And we can take each of these numbers, plug them into our quadratic equation. What this gives us, though, due to the nature of this plus minus term, are two different solutions for x. We have the positive solution, if you were to add the terms together, and we have the negative solution, if we were to subtract the terms from one another. All right, so the first term is a 0.252, and the second term, or the second solution, is the 0.086. Well, now you have two solutions, both of which seem to be reasonable numbers. How do you know which solution is right? Well, the easiest way to figure that out is to go back and remind ourselves what we were solving for in the first place. We were solving for concentration of H2 at equilibrium, concentration for I2 at equilibrium, and concentration for HI at equilibrium. And the first equation was a 0.1 minus x. Well, all we have to do now is observe our two solutions and ask the question, which one of these two gives us a reasonable answer? The first solution, the 0.252, if we were to plug that in for x, would give us a negative concentration, which doesn't make any sense in the context of reversible reactions. Negative signs here don't tell us direction. A negative concentration is meaningless. What that tells us is that our first solution, where we added the components together, in this case, yes, mathematically is a solution, but conceptually here is nonsense. The actual solution, the meaningful solution to us, physically and practically speaking, is the 0.086 concentration. So for x is equal to that, Well, now we have an actual way to calculate at equilibrium what our concentrations are equal to. 0.1 minus 0.086 gives us a value of 0.014 molar. Similarly, the iodine concentration, which was a 0.2 minus x, when we take our solution of the 0.2 and plug in the x value that we just solved, 0.2 minus the 0.086, gives us a value of 0.114 molar. And finally, our product concentration was a 0.1 plus 2x. So here we can take the 0.1, we're going to add 2 times our solution for x, the 0.086, and this gives us a value of 0.272 molar. So here now we have used ice tables laying out our initial conditions, predicting our change, and using that in combination with the equilibrium expression and K, we can find what our equilibrium concentrations for this reversible reaction are equal to. And again, this problem, this example problem goes through all of the steps. There are shortcuts. If you notice algebraic shortcuts, for instance, definitely you are free to mathematically take those shortcuts. If you can take a square root earlier, if you can combine things to solve for x easier, by all means go for it. If you can solve for x, right, solving for our x value here is the goal, because once we know x, we can calculate the equilibrium concentrations using x. Another way, though, that we can take a shortcut is going to be the next example, and it takes a little bit of like critical thinking to recognize when this shortcut is available, but if you kind of take a pause while performing these calculations, it should not be too hard to miss this shortcut. So let's look at one more example problem of using an ice table. These are going to be all of the examples in this portion of the lecture, but I will be posting a second bonus video solving 2 additional problems just so you can see this work a couple more times if that's going to be a little bit more comfortable for you. All right, so let's look at the most common simplification to solving an ice table problem that we are going to be using. And so the simplification is very simply this. If your K, your equilibrium constant, is sufficiently smaller than your initial conditions, you can drop the minus x step. Not all of the changes, but like the difference in initial conditions specifically. So let's look at what first sufficiently smaller means. So there are a couple of different ways that I've actually seen this being described using either percent differences or like multiple scalar differences. What we are going to use is our definition for sufficiently smaller, because this I think is the one that works the most consistently at the general chemistry level, is if your equilibrium constant K is at least 1,000 times smaller than initial conditions. All right, so if your K is at least 1,000 times smaller than initial conditions, we are going to be able to skip this drop minus x step, and I will lay out exactly where that comes into play in a second. So let's look at this second example problem. So we're starting with reactant. We have 2.4 atmospheres of it. Here we're looking at a Kp. So, just the slightly different situation where we're looking at pressures instead of concentrations. But again, the math all works out the exact same way. Now, we don't have any product. We have 0 of our carbon monoxide, 0 of our chlorine. So what this tells us, without even having to calculate a Q, is that our reaction is going to have to spontaneously shift from reactants to products, right? We have no product. And if we have no product, there's no way that the reaction could shift backwards. There's no way we could create more reactant from nothing. So since we are going to be shifting from left to right, what this tells us is that we are going to be losing some certain amount of our reactant, and we are going to be gaining some certain amount of our product. Now, the certain amount of our product that is going to be generated or reactant lost, whatever our value of x is, again, we do not quite know, but we can find it. So let's set up how do we find what this concentration is equal to? Well, we can already see that we've simplified our journey once already without even having to explicitly label it, right? Our change step, if we have 0 of a product or 0 of a reactant, the reaction is going to spontaneously move in the direction to fill that gap. So check, we've already figured out change. Equilibrium, therefore, is going to be 2.40 atmospheres minus X for the reactant and plus X for both of these products. Now, before setting up any type of complicated mathematic calculation, let's observe our K. Now we can see that our K here is very, very small, right? 10 to the negative 10. Our question, is this K at least 1,000 times smaller than the initial condition that we are presented with? And the answer here is most definitely yes. It is over 1 billion times smaller than the initial condition. Our K, 10 to the negative 10, is so much smaller than this 2.4 atmospheres. What this is telling us is that any change that could occur is going to be on this magnitude, is going to be of a small magnitude, so small compared to the initial conditions that with significant figures, our final answer at equilibrium, our concentration of the COCl2 at equilibrium is going to be approximately equal to 2.40 atmospheres. In other words, this change X is proportional to what our equilibrium constant is. And the smaller our equilibrium constant, the smaller this minus X is going to be relative to the initial conditions. Therefore, this minus X we can drop. This is the X that I mentioned earlier that we are allowed to drop. Up here, where I said drop minus X, this is the one that we are allowed to drop. Any change from the initial conditions, if this K is significantly small, it doesn't matter. Our equilibrium condition is going to be basically what we started with, because we started with so much, right? It's like taking a pile of 1 trillion marbles and taking one marble away and you're like, there, I've made a significant difference. You haven't. You still basically have, at eyeball, 1 trillion marbles. So that's what we're doing here. We are removing this minus X because the change is so insignificant. All right, so this is actually going to simplify our work a lot. So the way that we are going to simplify our work, or how this has simplified our work, we can set up our equilibrium expression. Our Kp, which we have the value it's equal to, is going to be equal to the partial pressure of CO times the partial pressure of Cl2, all divided by the partial pressure of COCl2. And I realize I said pressure or concentration over here. This should have been pressure. But the point still remains that the change is going to be so insignificant that our partial pressure will still end up being 2.40 atmospheres. So our K, our equilibrium constant expression, is going to be approximately equal to the partial pressure of our CO at equilibrium times the partial pressure of Cl2, all divided by 2.40 atmospheres. There. The partial pressures that we're going to be inserting here are the values at equilibrium, which we can see from our table are just values of X plus X. And the reason why we don't drop these X's here is because we are, do not drop, because we are changing from nothing, right? We have moved from 0, a number which signifies that you have nothing, to a number which signifies that you have something. This is, regardless as to how small the change is, a significant change. And for that reason, we do not drop these plus X's on the product side. So the X's are going to remain in the numerator, giving us an X squared, since we're taking X times X, all divided by 2.40. And this is going to be equal to our equilibrium constant, that 2.2 times 10 to the negative 10. Now, if we rearrange and solve this equation, it's going to be very easy to solve for X, right? We multiply the 2.4 up onto this side, and then we can take the square root of both of our numbers. That's way easier than trying to rearrange our equation into a quadratic and then use the quadratic formula to solve for X. Our X is going to be equal to 2.3 times 10 to the negative 5th atmospheres. So this gives us what our change is, what our X is equal to. And again, if we come up and observe our initial concentration or our initial pressure, partial pressure of the COCl2, 2.40 minus a number that is times 10 to the negative fifth with rounding to significant figures is still going to be equal to 2.40. So this atmosphere at equilibrium for the COCl2 has not changed. However, we do have a partial pressure now, both for the chlorine and for the carbon monoxide, both values being equal to X, which we just solved for. So now we can see that there is a slight shift from reactant to product, that slight shift giving us 2.3 times 10 to the negative fifth atmospheres of each of our products, whilst also simultaneously not really shifting that much away from the reactant due to the very small nature of our Kp. All right, and with that, we are going to call it a day. So here we have a couple of example problems, equilibrium and free energy. So this is going to be a delta G type of a problem, equilibrium concentrations. These will be like our ICE table type of problems. Now, I will be working through a couple of additional examples in a bonus video. So if you're already feeling comfortable with this type of problem, I'm not going to waste your time. But if this is something new to you, I would definitely encourage you to watch that video. I'll be working through a couple of different ways to work with ICE tables, just so you can get some more experience, some more examples, worked out in front of you to make you more comfortable with this type of problem. But with that, let's see, homework is going to be posted corresponding to this lecture on Monday, which will also then be due on Wednesday at 11:59. So do not forget about those Connect assignments. They are still ongoing. Let's see, no other big announcements for the day.